Welcome to this video on buses in computer systems. In this session, we will explore what buses are, their role in the functioning of your computer, and how they enable efficient communication between the different components of your system. Whether it is transferring data between the CPU, memory, or connecting external devices, buses are a fundamental part of how computers operate. The main job of a bus in a computer is to provide a pathway for data transfer. It connects the processor, memory, and input-output devices so they can share information. A bus protocol is a set of rules that controls how devices on the bus communicate. There are three main types of bus lines: data lines, which carry the actual data, address lines which tell where the data should go, and control lines which manage how data is transferred. One important control signal is the read-write signal. When the signal is set to 1, the bus performs a read operation to get data. When it is set to 0, the bus performs a write operation to send the data. Bus control signals also carry important timing information. This specifies when the processor and the input-output devices can send or receive the data on the bus. There are different ways to handle the timing of data transfers, which can be classified as synchronous or asynchronous. In every data transfer, one device acts as the master. This is the device that starts the transfer by using read or write commands. The master is often the processor, but other devices with the DMA capability can also take control and become the bus master. The device that receives the data or responds to the master's command is called the slave or the target. In a synchronous bus, all devices connected to the bus share a common clock signal so that ensures coordination between data transfer. The timing of all operation is dictated by this clock, which produces evenly spaced pulses. These pulses define distinct time interval known as bus cycles, during which specific activities like reading from or writing to a memory location or input or output device can occur. Key features of synchronous bus include common clock line. All devices derive their timing from a central clock, ensuring synchronized operations. Fixed time intervals. The clock pulses create uniform intervals, allowing for predictable timing in data transfers. Bus cycle. Each clock, each clock pulse interval represents a bus cycle, and during this cycle, one data transfer operation can take place. In a synchronous bus, address and data lines can be either high or low at the same time. Different lines can represent different values simultaneously, allowing multiple bits to be transmitted at once. This representation helps visualize the bus activity, making it clear that some lines are high while others are low, depending on the data or address being sent. Crossing points are where lines changes from high to low, vice versa. These points indicates when new data or addresses are being transmitted. These changes are synchronized with clock signal, ensuring all devices the bus operate together. Sometimes a line may not clearly be high or low. This is called intermediate state, shown as a level halfway between high and low. This can happen during transitions or when the line is not being actively driven by any device. Asynchronous bus is a data transfer system that uses a handshake mechanism instead of a common clock signal to control communication between devices. Here is how it works. Handshake mechanism. The bus relies on a handshake between the master device, which initiates the transfer, and the slave device, which responds to the master. This ensures that both devices are ready to communicate. Instead of a single clock signal, the asynchronous bus uses two control lines. Master ready. This signal is set to high by the master to indicate that it is ready to start a data transaction. Slave ready. This signal is sent back by the slave to indicate that it is ready to receive or send data. Data transfer process. The process begins when the master asserts the master ready signal. Once the slave is ready, it asserts the slave ready signal. Only when both signals are active can data be transferred safely between the master and slave. The timing signal T0, the master places the address and command information on the bus, and all devices on the bus begin to decode this information. At T1, the master sets the master ready line to 1 to inform the input output devices that the address and command information is ready. At T2, the selected slave having to decode the address and the command information performs the record input operation by placing the data from its data register on the data lines. At the same time, it sets the slave ready signal to 1. At T3, the slave ready signal arrives at a master indicating that the input data are available on the bus. At T4, the master removes the address and command information from the bus. And finally, at T5, when the device interface receives the 1 to 0 transition of the master ready signal, it removes the data and the slave ready signal from the bus. This completes the input transfer. In this case, the master places the output data on the data lines. At the same time, it transmits the address and command information. The selected slave stores the data into its output buffer when it receives the master ready signal and indicates that it has done by setting the slave ready signal to 1. Full handshake process involves a change of state in one signal followed by a change in the other signal. The steps involved in the full handshakes are: the master asserts master ready. The slave, upon detecting this, captures the data and then asserts slave ready. The master recognizes the slave ready signal and can proceed with the next operation or release the data lines.